Hi there. This video is going to give you an introduction to the different types of bonding you'll encounter in chemistry. We're going to focus our discussion this semester on covalent and ionic bonding examples, okay, and we'll save metallic bonding for later. Covalent bonding is when two atoms share electrons in order to form their bond. Ionic bonding is when one atom gives an electron or more than one electron completely to another atom. So for ionic bonding, what you end up with are ions that are coupled together in a large lattice network as shown here. Okay, so each individual unit, okay, so an NaCl unit, okay, would be the single bond between, ionic bond between sodium and chloride. And then you would have a lot of these single units grouped together and associated electrostatically, right, where their positive and negative charges coordinate with one another, okay, into what we call a lattice structure. So this would be our lattice. So for an ionic compound, we're not generally referencing individual molecules of sodium chloride, okay, we reference individual units of sodium chloride or whatever the ionic compound is, with the understanding that this entity does not generally exist on its own. It exists in the form of this larger scale lattice where you have a lot of those units grouped together. One of the hallmarks of an ionic compound is that when you dissolve it in water or another solvent that it's soluble in, it breaks up into its component ions. So when you put a chunk or a crystal of sodium chloride into water, like when you're cooking pasta and you put some salt in the water, those salt lattices will start to break up into the individual ions. So what you'll have floating around in your water are individual sodium plus ions and individual chloride, Cl minus ions. Okay, now those are all going to be, we'll see later, they're going to be associated with a bunch of water molecules, okay, but they will break up into their separate ionic part. Okay, so ionic bonds will break up into individual ions in water. Okay, it's an important characteristic of ionic compounds. Molecular compounds or covalent bonding compounds don't break up when you dissolve them in water. So they stay in their molecular form when you dissolve them. Okay, so we would call these kind of molecular types of compounds. Okay, so they stay, didn't mean to erase that. So they stay as molecules when you dissolve them in water. All right, so those are two of kind of the major differences between an ionic compound and a molecular or covalent compound. Okay, so ionic compounds are going to break up into ions in water. Molecular compounds stay in that molecular form when you dissolve it in water. This gives rise to a number of other different characteristics of these types of molecules. Okay, so again, ionic bonds are very, very strong. They're one of the strongest bonds that you'll encounter. Okay, so that means that it takes a lot of energy to break those bonds. Okay, so when we think about things like melting points or boiling points, okay, it's going to take a lot of energy, aka a lot of heat, to break those bonds and melt or boil your ionic solid. Okay, so ionic compounds like sodium chloride will tend to have very high boiling points. Molecular compounds, on the other hand, tend to have relatively low boiling points in comparison to ionic solids. And that's because these covalent bonds are relatively weak in comparison with the strong electrostatic ionic bonding that you have for your ionic compounds. Okay, so we will encounter some of these differences as we go along and talk about intermolecular forces later on in the course. But for now, this just gives you an idea of the different types of bonding that you can encounter in chemistry and some of the major differences between covalent and ionic compounds. Okay, so one skill that you need to develop is to be able to predict what kind of bond a molecule is going to have. Okay, so the way that you're going to do this is to take a look at how much your atoms want to share electrons between each other. Are they going to want to totally donate electrons from one to the other, okay, which would be our ionic picture, okay, where sodium completely donates an electron to chlorine, okay? Are they going to share electrons in a form of covalent bond, okay, is your other question. Now, if they decide to share electrons, you need to figure out how equally are they going to share them? Are they going to share them exactly equally, where each atom has exactly the same pull or ownership over the electrons that they're sharing? Or are they going to, or is one going to want to have the electrons more than the other? Is one going to have a little bit more pull over the electrons than the other atom? Okay, that case would be what we call a polar covalent, okay, where we have uneven charge distribution. Okay, and the previous example would be purely covalent, where you have even charge distribution, where each atom has exactly the same pull over the electron. One designation that you're going to see labeling a lot of these types of figures or ways that you draw a bond are these notations that you see up here. These little things that look like D's or squiggles. Okay, these are Greek deltas, and we say that's a del plus or del minus or delta plus, delta minus. Okay, and those just indicate the relative partial charge on your covalent bond. Okay, so this gives us a sense of how is that charge distributed in your covalent bond. Okay, so for Cl2, right, there's no uneven charge distribution, okay? Each atom has equal share over those electrons, okay, so we don't really label a partial positive or partial negative here because there isn't one, okay? But when we go down to our polar covalent example for HCl, we see that the chlorine has a much larger pull over the electrons than the hydrogen, okay? So how we would indicate that would be to say that we have a partial positive on the hydrogen and a partial negative on the chlorine. Okay, so you'll be able to designate which one should hold the partial positive and which one should hold the partial negative based on the relative electronegativities, which we'll talk about next. Okay, so whichever one has the larger electronegativity is going to get that partial negative charge. There's clearly a gradient over which these electrons can be shared. Okay, so we kind of have systematic cutoffs for when we say something is purely covalent, polar covalent, or ionic. The tool that we use to determine those cutoffs is the electronegativity of our atoms. So one thing that you'll want to have handy as you're starting to become acquainted with whether your compound is ionic or covalent or purely covalent or polar covalent is a table of electronegativities. Okay, so this is one example of a periodic table that shows you the electronegativities of the different atoms that you might be interested in. Okay, so our cutoffs for an ionic compound is you're really looking for a difference in electronegativity of greater than 2, okay, is going to be ionic. Okay, and if you're between 0 and 2, that's going to be polar covalent, where you share those atoms unevenly. Okay, and then if you have a difference in electronegativity of about 0, okay, sometimes you might have a little tiny bit of a difference, but we'll say it's about 0, that's going to be what we call our purely covalent situation. Okay, so these are general cutoffs that you can use to predict whether or not you're going to have an ionic compound, a polar covalent compound, or a purely covalent compound. Okay, and all you're doing is looking at the differences in the electronegativity values. Okay, so if we look at the example for sodium chloride, okay, so if we want NaCl, we want to look at the electronegativities for sodium and chloride. So zoom in here so I can see it. Looks like sodium is 0.93. Let's put that on top there. Okay, and then if we go over to chlorine, we see 3.16. Okay, so let's see if we can predict that we'll have an ionic compound, like we've already said. Okay, so the difference in electronegativity for sodium chloride, 2.23. Okay, so clearly greater than 2. So we know that that is going to fall under our ionic category. Let's look at the other example from the previous slide. So we just looked at sodium chloride and verified that we're going to have an ionic bond, which means we'll have complete transfer of that electron. We had a delta En, or difference in electronegativity, that was greater than 2. Okay, let's look at HCl, which this table tells us should be a polar covalent bond. Okay, so we want to look at HCl. So H looks like 2.2 for an electronegativity, and then we already looked up Cl. We saw that was 3.16. Okay, calculate the difference in electronegativity for those two atoms, and we get a value of 0.96. Okay, so 0.96 falls under our polar covalent situation. So we have a change or a difference in electronegativity that falls between 0 and 2. Okay, so as predicted, we have a polar covalent bond for HCl. Okay, our other example from our slide before was Cl2. Okay, so let's see if we can verify that Cl2 should be a purely covalent compound. All right, so going back here, we want Cl2. So can kind of say ClCl. Okay. Again, we've already looked up that electronegativity value, so you get 3.16 and 3.16, and hopefully you don't have to do any math here to see that that is 0. Okay, so whenever you have the same atom in your bond, okay, you know right away that's going to be a purely covalent, or what we call a non-polar covalent bond. Okay, so you can normally we'll call this a non-polar covalent or purely covalent. Okay, so hopefully this helps you to feel comfortable with determining whether the bond you're interested in is polar covalent, non-polar covalent, or ionic. Down the road, that being able to make these predictions is going to be really important in helping you to predict the expected behavior of your compound. Okay, that's it. Hope that was helpful.